Today we're going to talk about distributed file system design and in particular NFS. So here's a diagram showing a typical setup in a distributed file system. There are multiple clients and they access through the network a server that holds the files. The server could be very simple. It could be just a single physical machine that holds the files, or it could be more complicated. There could be multiple servers that provide replication for higher availability, and also the server could have on the background some kind of distributed storage system. Today we're going to mostly be concerned with simple file system design where we have multiple clients and a single server. So how do you go about designing a distributed file system? You typically have a few design considerations in mind. You want to provide location transparency. Location transparency has to do with how do you find the server. Do you have to know its DNS name or IP address, or there's some other scheme that does not require you to know this information. Whether the server is stateful or stateless, a stateful server keeps track of the operations that are ongoing, so that if it crashes it can continue doing an operation that was interrupted. A stateless server does not keep track of this information and relies on the client to re-execute the requests if the operation was interrupted by a crash or a network failure. How does the system handle failures? What about caching? Do we cache files either on the client or on the server or elsewhere? And if we do cache, how do we ensure cache consistency? So location transparency, if we have complete location transparency, the client is unaware of the server location. And so the questions that arise is, how do you name a remote file? Is the name structure different from the local file? And do you include the name of the server in the file name or not? And existing file systems have traditionally used both designs. In NFS, the location is completely transparent. Basically, you access a file located on an NFS server in exactly the same way as you would access a local file, and the operating system hides from you the fact that when you access the file, the request is actually being shipped to a remote server. And that is very convenient because the applications do not need to be changed. However, if a system fails, then sometimes you might be taken by surprise that you're accessing a file and your whole application freezes because you're simply were unaware that you're accessing network in your application. When you think about handling failures, you have to assume, you have to have a failure model. You have to have some assumptions behind what failures can happen. When we refer to server crash, this is fail stop failure, and when that happens, the data that's in the server memory can be lost. And to protect ourselves from this type of failure, the server may write to the local disk and send before it sends acknowledgements to the client. We have to be careful when we do that, because when we write the data in the file system, when we perform a simple write operation, the data doesn't always go to disk right away. In modern operating systems, it is written into the buffer cache, and then later, at a later point, it is actually flushed to disk. So we have to keep that in mind. And another type of failure that we usually expect with distributed file systems is, of course, message loss, but that is typically taken care of by the underlying protocol that transfers the data between the client and the server. In the case of NFS, this is the RPC protocol. Systems like NFS don't make any special provisions for Byzantine failures and other more complicated failures than these two. So as I mentioned, the stateless server would lose the state of the file system that has not been saved to disk in an event of a crash. So basically, a stateless server looks to the client like a slow server, because a stateless server would basically is expected to recover quickly, very quickly after reboot, so the client is expected to maintain the state, and if the server has crashed, the client would simply resend the operation, and the server will do it again. But that assumes that the file operations must be idempotent, meaning that if you execute the same operation twice, you still get a correct result. Because when a server is stateless, if a server crashes, you don't know whether the operation that you previously sent has succeeded or not. So if you're re-executing the operation, you must be prepared for the fact that you might be re-executing the same operation twice. What is an example of an idempotent operation? So writing a particular specific block of a file is an idempotent operation, because if you write the same location of the file with the same data more than once, you get the same result. What is an example of a non-idempotent operation? Append. If you're appending to a file, if you append the same data twice, or 3 times, or 4 times, you will get a different result every time. Every time you will get either 2 or 3 or 4 copies of the same data at the end of the file. So that's why NFS version 3, which is the stateless design protocol, did not allow append operations. NFS v4, which actually departed from statelessness and became more stateful, began to allow append operations. So stateful server remembers its state and recovers from failure. So it's a more complicated file server design, and assumes longer recovery times, but it permits non-idempotent operations. In today's talk, we're going to mostly cover NFS v3, so it assumes a stateless design. Caching is important in file systems because file access exhibits temporal locality, meaning that if you access a part of a file, it is very likely that you will access it again soon. And so caching is about keeping a recently accessed part of a file or the entire file close by to where it was last accessed. So caching can be done at different points in a distributed file system, at different places. So it can be done in a client's memory and a client's disk. It could be done in a server memory, or it can be done somewhere inside the network, known as proxy caching. And various distributed file systems have used all these locations for caching. Also, caches typically anticipate future accesses by in the file by doing a read ahead or prefetching. If you have a cache in a distributed file system, you have to be worried about consistency. Consistency is about ensuring that the copy of the file is up to date. And consistency issue arises when the file might be modified in the cache but not at its true source. So even if we have a single file, a single client, suppose that a client modifies the file in its cache and the client copy becomes different from the server copy, and then the client crashes before propagating the changes, so the data will be lost. So what do we do to avoid this kind of situation, or to minimize the probability that our data will be lost? Right? This is an important design consideration. And of course, consistency issues also arise when we have multiple clients sharing files. So if client A and B share files and clients cache the files, the client A might modify the file in its local cache, and the client B doesn't know that. It contacts the server and it sees the outdated copy of the file. So what do we do to prevent reading outdated copies, or at least minimize the window when the clients see outdated copies? That's an important design consideration as well. So consistency protocol is an algorithm that determines when we propagate modified changes back to the server, or maybe in some more elaborate protocols we might even exchange the modified data between the clients. But basically a consistency protocol answers the question, how do we maintain file copies consistent? Typically we have two design schemes. Write-through is instant propagation. As soon as the client changes the data, it propagates it to the server, and that reduces the risk of data loss and crash, but it may result in a large number of messages. And a write-back, which is more typically used for file systems, it's delayed propagation or lazy propagation. Basically, a client propagates dirty data when the file is closed, or after a delay, or on some other event, such as a specific commit request from the user. So this results in a smaller number of messages in a consistency protocol, but of course incurs a higher risk of data loss. So consistency protocols become interesting when files are shared, and as we mentioned before, when files are shared, one client may modify the data, causing the data to become inconsistent. And so the approaches in this case are client validation or server validation. In a client validation, the client contacts the server for validation, so it periodically asks the server whether the data has been changed. And server validation is when the server notifies the client when the cache data becomes stale. So in that case, of course, the server design becomes more complex, because the server must keep track of what clients are using the file, and so this automatically implies a stateful server, and the server needs to notify these clients when the data changes, so it adds a load to the server. Another design consideration is granularity of data access. When we read or write some amount of data from a file, do we just ask the server to perform operation on this specific number of bytes, or do we operate in larger chunks? And because we don't want to send around too many protocol messages, we usually don't operate on the granularity of bytes. We operate on the granularity of blocks or entire files. So we looked at design considerations, and how do we make decisions about designing a distributed file system? How do we know whether we use a stateful or stateless server? How do we know whether we use block granularity or file granularity? How do we know whether or not to do caching and where to do it? And of course, to answer these questions, you need to understand how your file system is being used. And for a very long time, design of distributed file systems has been driven by a study that was done by Mary Baker, who was at the time a PhD student at UC Berkeley and now is a researcher at HP Labs. And her study examined the usage patterns of files in an engineering university environment. And her study found the following things. Most files are small, and read operations are much more frequent than write operations. Most accesses are sequential, random accesses are rare, and files are usually read in their entirety. Data in files tends to be overwritten often, and most files are read and written by one user. And when users share a file, typically only one user modifies the file. Fine-grained read-write sharing is rare, and file references show substantial temporal locality, meaning that if you access data in the file, you're very likely to access the same file again very soon. So how do we take these usage patterns and our design considerations and merge them together to come up with a good distributed file system design? So let's try to see how NFS designers have tried to do that. NFS is a network file system. It was designed in the middle of the 1980s, originally developed at Sun Microsystems. It is in a widespread use in many organizations around the world. Its key features are access and location transparency even inside the operating system kernel, and we'll see what this means in a second. File access and caching is done on block granularity. NFS uses delayed update propagation, client validation. Up to NFS v3 we have a stateless server, and we have weak consistency semantics. So let's go over these features in a little bit more detail. How do we provide access transparency in the NFS? So a Unix file system implements what is known as virtual file system. So basically, if you perform an operation over a file system, either from a user application or even inside the kernel, so you want to open a file, you want to read or write, you don't care which type of file system you access, whether it's FFS or XFS or NFS or what have you. So you simply perform the operation against the virtual file system, and then the virtual file system knows how to translate this abstract operation into a specific operation corresponding to a particular file system that is plugged into VFS as a kernel module. So when you want to access an NFS file system, you access the file system as you would any other local file system, and then VFS redirects the request to the NFS client, and that in turn contacts NFS server using the remote procedure call protocol. So Unix file systems typically cache file blocks that are accessed by application. So this is called a virtual file system cache. And it is convenient for NFS to take advantage of this caching that already exists in the operating system. And this VFS cache dictates that we cache blocks of files, and typical block size is 8 kilobytes. So that, in some sense, places a requirement on NFS to use block granularity for file access. It's not a requirement, but it's simply more convenient to do so. And so files in NFS are cached on the client in the client's memory. They're not cached on disk. So NFS uses existing operating system buffer cache to cache blocks of files that are accessed over NFS. The actual copy of the file lives on the server, but a cached copy of the blocks that were accessed live on the client in the virtual file system buffer cache. So NFS accesses and caches files on block by block granularity. So if you start reading first few bytes of the file, the client will bring in the first block. But from Mary Baker's study, we just learned that most files are accessed in their entirety. So isn't it inefficient? In order to maximize the network bandwidth, isn't it better for us to fetch the whole file rather than the first block? So NFS designers recognize that as a potential performance problem. So what NFS protocol does to account for that is prefetching to anticipate future accesses from the client. And prefetching basically assumes that the file will be accessed sequentially and in its entirety, but it starts out modestly. So when the client accesses the first file, we fetch, instead of fetching just one block of that file, we prefetch a couple of blocks. But if the client continues accessing the file sequentially, NFS prefetches more and more blocks. Client caching in NFS uses delayed propagation. What it means is that updates to file blocks that are cached on the client are not propagated to the server immediately. They're propagated either when the file is closed, or when an application explicitly calls sync, or whenever an operating system flush daemon wakes up and goes over the VFS buffer cache and flushes the dirty blocks to the corresponding file system. This is when the data is actually sent to the server. So therefore, clients accessing the same file may see inconsistent copies. So if client A made some changes to the file and they have not yet been propagated to the server, and then client B goes and reads that file, it may get stale data. And so to maintain consistency of some sorts, NFS uses client polling. Client polling is based on two timestamps. TC is the timestamp when the cache entry was last validated at the client, and TM is the timestamp when the data was last modified on the server. And client polls the server at intervals that range somewhere between 3 and 30 seconds. That is a tunable parameter. And a cache entry, a file block that the client has previously read from the server, is considered valid if the time that has elapsed since the last polling has not exceeded our interval t, or if the client recently received the TM timestamp from the server and that timestamp is the same than the last remembered copy on the client. Basically, the server tells the client that the data has not been modified since the client last requested it. If the client polling is done very frequently, it can result in significant overhead. So NFS takes some measures to reduce polling overhead. When a client receives a new TM value from the server, which is the modified timestamp for a file block, the client applies it to all blocks from the same file, not just that one block. And that makes sense because we know that files are typically accessed in their entirety, and also there is good spatial locality in file accesses. And also the modified timestamp for file F is piggybacked on all server responses for all operations on file F, so that the client doesn't have to send separate messages to retrieve that timestamp. A polling interval T is set adaptively for each file depending on the frequency of updates to that file. And typically the polling interval for directories is larger, 30 to 60 seconds, because directories tend to be modified less frequently than regular files. In addition to client caching, there is also caching on the server. So when a server reads the file from its local disk, and before it sends it to the client, the block that it has read also gets placed in a local buffer cache on the server, in the server memory. And that makes behavior in the presence of failures interesting. So writes to the local file system essentially also use delay propagation. So let's say that the client sends the data to the server. So the client modifies a portion of the file, it sends the data to the server. The server writes the data into its VFS buffer cache, and typically the data does not go to disk immediately, right? We remember that when the data is in the VFS buffer cache, the flush daemon writes the dirty data to disk only periodically, every 30 seconds or so. So how should NFS client and server interoperate in the face of server caching and potential failures? So the first option is when the client writes the data to the server only sends acknowledgments to the client after explicitly flushing the data to the local file cache, but not to disk. So the server, not flushes, but writes the data to the local file cache, but not to disk. The advantage of this option is we have a fast response to the client, but if the server crashes before the data is actually flushed to disk, the data may be lost. And the second option is that when the client writes the data to the server, the server explicitly syncs or flushes the data to disk and then responds to the client. The advantage is that the data is not lost if the server crashes, but the disadvantage is that each write operation takes longer to complete. And if we have many clients performing writes to the server, then the server has to perform a lot of random writes to disk, and this can limit server scalability. So how does NFS solve this problem? All the NFS versions, and I'm referring to NFS versions before v3, so v1 and v2, used the write-through protocol, so that's option 2, meaning that every time the client writes the data to the server flushes it to disk before responding to the client. And not surprisingly, this was recognized as a performance problem. And NFS v3 introduced a specific commit operation. So client can ask the server to flush the data to disk by sending the explicit commit operation. NFS server is stateless. It forgets its state when it crashes. A local file system recovers local file system state if it was made inconsistent because of a crash. So NFS server does not have to worry about anything about leaving the file system inconsistent, because that's the job of a local file system. So, but then the burden to recover from failure basically remains on the client. So if so the client typically just keeps retrying the operation until the server reboots. And so if the client sent an operation to the server and the server hasn't responded, the client will simply try again. And the client doesn't know whether the previous operation has succeeded or not, because the server, if it simply wrote a block of a file, when it reboots, it doesn't remember whether it has sent a response to the client, that this operation was completed or not. So what this means is that all file operations must be idempotent. So when we read or write an entire block of a file, this is idempotent, because if we read a given block, we can read it many times over and over again, we will still get the same result. If we're writing a file block, which means a portion of a file of a particular size at a particular offset, if we write it many times over, we still get the same result. And creating, deleting files is also idempotent, because if we try to create a non-existent file several times, the first time it will be created, and the second time the local file system simply won't allow us to create it again, because the file with that name already exists. So this is by definition idempotent. But like we mentioned before, appending is not idempotent. So that's the key features of NFS, and that's all I have for today. Thank you very much.